carried with you. So when the person walks into a shop, they know who they are and what kind of a quality of, or what kind of styles do they like. You know, when he walks into the car, the temperature gets set the right way they want, and the car recognizes you and things like that. So, and then there is a lot of thin devices. Devices that are thin in computing and storage, that size 90%. And you know, it's increasing all the time. And what this means is, if you have thin devices that you're carrying with you, and computation is happening somewhere else, it's all about connectivity, wireless connectivity. The more wireless connectivity, the better wireless connectivity is what's going to make this happen. There's many different things which is required. But the part that I know more about is wireless connectivity. And that shows that, you know, there is a good indication that there's a great use for that going forward. So the next generation of the wireless devices is required. Today, wireless is about what? It's about convenience. It is about the fact that you can move around and get the information, but it's not about quality. So usually if you want to use something quality, use a wired connection. Wireless is all about convenience. But going forward, if you want to do your video conferencing in the bus and stuff, and make sure that the quality of the communication is not sacrificing, that wireless quality has to go up. And the next generation of devices has to happen. And we believe that Wi-Fi, or 802.11, is positioned to make this happen. And I'll go through that, why that is the fact, or why that's the perception, at least from our point of view, and we're betting a lot on that point right now. So, talking about wireless connectivity. There are many different standards, and they have been evolving over time. They're covering various applications, and they're complementary. You got the wireless WAN, you got wireless LAN, and wireless personal area networks. All they have their own needs. And how they're different is, there depends on the application, what you need. Do you need the throughput? Do you need the low power consumption? Is it the service, or is it the basic connectivity of the devices inside the home? Is it outdoor? Is it indoor? That's what's going to make a determination what kind of a wireless you will use. So, if you look at it a little bit more details, you know, you got at one end, you got technologies such as RF, near field communication, RFID, either one of those, which is meant about very low throughput, very low range, but for very basic data exchange. So very low power, you know, like when the lady walked to close to a location, they knew who she was. That was probably using this kind of a communication. It is an unlicensed band, so you don't have to pay a service for it. It is something that you can put in every device without dealing with a service provider. And it has its own target devices, like smartphones, laptops, PDAs, ATM machines, vending machines, and so forth. That is about, you know, very short communication, short distance communication, but very low throughput, very low cost. Then you got Bluetooth. Most of you guys have Bluetooth in your devices, in your phones, in your speakers, and so forth. It goes a little bit farther, a little bit higher throughput. It is meant for the data networks or the sound transfers. It's not really meant for video, which is going to be majority of the communication going forward. But it has its use in laptops, keyboards, scanners, phones, printers. It is, again, it's unlicensed band. We have Wi-Fi. Goes up to 3.2 gigabits per second in the future standards. And I will talk about why is that and how is that. And goes up to 100 meter. It's a little bit wider range. It's about connecting anything inside your home that it needs, it can be connected to the internet or to the other devices. So it does data communication, is going toward doing video. Quantana was the first company who showed that we can do video over Wi-Fi, and it's going to be more of that going forward. It is, again, an unlicensed band, and many devices can benefit from that. You got LTE, or any kind of a cellular technology. LTE can go up to 500 megabits per second, goes a wide range, 10 kilometer. The difference here is it is a licensed band, so you do have to have a service in order to subscribe to this. You're not going to put this inside your TV. You're not going to put this inside your DVR. because you don't want to have a service pay a monthly fee to the service provider so your TV gets connected to your DVR, right? So it has its own application. It's inside your cell phone. It could be inside some of your laptops, but not inside everything. It's more voice-centric and has limited video type of usage. My talk is going to be more concentrated against around Wi-Fi. And why is that? Well, it's because we think there's a dominant interface going forward, but also because I know that the best. So I couldn't be talking about everything here. You know, it will take a different set of experts to talk about those. So an overview of the Wi-Fi. Let's start with the history a little bit. In 1997, it's hard to read, I think. Well, believe me what it says. I try to remember myself too. It was 802.11 came out. It was only 2 megabits per second. Very low throughput, very low range. Then we had 11B coming out, went up to 11 megabits per second. 11A and G almost came out around the same time. One uses 5 gigahertz, one uses 2.4 gigahertz. Took the throughput up to 54 megabits per second in 2003. Then we had 11N. 11 is an interesting beast here. Why is this? First of all, if you look at it, it has throughputs as low as 11G, and it goes all the way up to close to actually 600 megabits per second. And it covers a wide range of standards. It has both 2.4 gig and 5 gig as part of the standard, and has a lot of different options, which enables you, if you want to build a very low-end device, a device that is cheap in cost and in power consumption, you can use the options in the standard that you will be here. And if you want to take it up and make it a very strong device that you can have very high performance, a high throughput for the application which requires that, you can build that with 11N as well. You can build in 2.4 and the 5 gig. Then we have 11AC, which is coming out. 11AC is to be the official standard in end of 2013. There are already devices pre-11AC standard out there. But 11AC is even a wider range than 11N was. It is a little bit better than 11N in the lowest range, or pretty close to that. And it goes up pretty high. And you know, the first generations will use 80 megahertz of bandwidth, they will be here. And the next generation devices can go up to 160 megahertz of bandwidth, and they will be there. It can cover up to 3.6 gigabits per second, which is much higher throughput than what we ever had. But the first generation will be about, at best case, about 1.8 gigabits per second at 80 megahertz bandwidth. And that is to come out next year, even though devices are out there, and the standard is pretty clear today what it's going to be. So it might be minor modification. Most of us are betting on building devices, and will be only software change going forward. But the hardware should be pretty close to what is required in the standard, final standard. If I looked at these standards and evaluate them as performance, which is megabits per second, versus range. See where they fall in the standards. 11B was very short distance communication, very low performance. 11B got a little bit better, sorry, that was 11 without any letters afterward. 11B got a little better in performance and the throughput. It could, as I mentioned, was 11 megabits per second to about 115 megabits per second feet in range. The third generation, which was 11A and 11G, they covered up to 150 feet, 54 megabits per second. Now, 11N, again, interesting phenomenon. You can be a little bit better than 11A or G at a one-by-one device, which is one transmit antenna, one receive antenna, with just a very nominal, or none of the optional portion of the standard implemented. And you can be as good as, significantly better, by a 4x4 device, which has all the other options implemented as well, and which I cover what they are. And 11AC will have even a bigger spot here. So you can build 11AC, which is lower performance than many of the 11N devices and lower range than many of the 11N devices, and or you can take it all the way up. And really depends if you look at a device which says 11AC, not necessarily the throughput of it is clear. So I wouldn't judge the standard by just the naming of it, and what you're going to get for a product. And this is something that different vendors will have different ways of deciding what they're going to make, depending to the applications they're going to go after. And the standard is designed on purpose like this because it gives you the opportunity to be the very low-end device that you want to put a very short range communication, or very high-end device that you want to make sure you guarantee the quality of the service of a video communication. And depends to that, what you're going to build is determined by that. So quick comparisons between these. Again, 11A is using 5 gigahertz. 11A never really took off. 5 gigahertz at the time was an odd band. There were not many devices with the 11A which came out and got deployed. 11B and G in the 2.4 gigahertz, they had a lot of deployment. That's the dominant deployment you see out today in many different devices. 11N, when it came along, it allowed both 2.4 and 5 gig, and actually that's when the interest in 5 gig became dominant, and that's when actually 11A took a piggyback with 11N. 11AC going forward is only 5 gigahertz, no more 2.4. 2.4 is too crowded. Too many devices are out there and too little band to use. 5 gigahertz gives you an opportunity to expand your band. It is almost 3 times more channels available, or 4 times, 3.5 times more channels available in 5 gigahertz than there are in 2.4 gig to be used. The bandwidth was about 20 megahertz till 11N came about, became 40 meg. And in 11AC, you have both 80 and 160 added as well, so much wider bandwidth. Number of the streams, the MIMO systems. So you can communicate simultaneously, and I will describe what that means. Simultaneously, same data, different data over the same frequency over the air, and use the diversity property of the channels to get more information through. So 11N allows up to 4 streams, and 11AC allows up to 8 streams, so it's pushing the throughput higher. And the number of the data rate per stream went up from 54 to 150 here, and 433 in 11AC. Most of these guys are OFDM versus except 11B, which wasn't. And 11AC is also using a special diversity, multi-user MIMO. So I'll cover a little bit what that means. So talking about 11N a little bit. So what is new in 11N? We added MIMO. So you can send more than 1 stream at a time. And I will describe what that means. We added beamforming. You precondition the channel, so when you're transmitting, you can have very simple equalizers to get close to the optimum demodulation or equalization. Channel bonding went from 20 megahertz to 40 by putting 2 channels next to each other. Shorter the guards between each frame, so this way, or each symbol. Each way you increase the throughput by putting some more constraints on the receiver. Frame aggregation and better MAC was another improvement which was done. A more efficient OFDM, use more tones than you did before, less guard bands again. And we use a space-time block coding in order to utilize more of the diversity of the channel. It's useful when you don't have beamforming. Added a new forward error correction code, LDPC, low density priority checking, and concurrent communication in 2.4 and 5 gig, as I mentioned before. So, how does a MIMO work? You have, in here we have an example of a 4x4 MIMO with 4 streams and unequal modulation. Basically, if you have a N by M MIMO, you have N transmitters and M receivers. Signal from each of the N transmit can be received by each of the M receivers. We have different paths over the channel. So here you have 4. The signal is going through these 4. Here it shows the signal, goes through the 4 antennas out. Through the channel gets really convoluted, and you see that in each location of the receiver, you see the multiples transmit signals. So each receiver sees the sum of these transmit signals multiplied by the function of the channel. And the job of the receiver is to clean them up and get the original signals back on again. But if this channel has a higher rank than the number of the transmit signals, it can decode those many streams orthogonally, in parallel. So the actual, depending to the rank of this channel, the information transmit can increase. So information transmit is dominated by two factors. One is how many transmitter and receivers you have, which at minimum your rank of your system is based on the number of channels. And this is, you don't want to have, I mean, if you have a channel which is very well ranked, you can take the opportunity of that by having more transmitter and receivers and carry more information through. The other thing about 11N is digital beamforming. Given that you have a channel which is pretty diverse, by preconditioning the signal ahead of time, you can make equalizers which are very simple and linear and have the optimum equalizer. Beamforming does that for you. If you had one stream in a line of sight communication, so I could see my transmit could see my receive, in that case, beamforming converges to transmit the energy to that direction. But in real scattering environment, in an indoor scattering environment, beamforming is basically doing the pre-equalizing of the channel. Also, what beamforming can do is it can cancel the energy in the directions you don't want. So in this case, is maximizing the energy toward this one station from this access point. In this case, it's maximize energy to this access point, this station, while it's minimizing energy to other station. So those are the benefits of the beamforming. We have run some curves to look at what is different from same 11N to the same 11N. The point of this is not to go too down technically, but the point is to show that, you know, this is a 2x2 system. It requires a lot more SNR, signal to noise ratio, in order to communicate. And this is still an 11N system. Here is a 4x4 11N system with a digital beamforming. Both of them 11N, but this one does significantly better than this one, about 25 dB better, compared to a 3x3 MIMO system, a 4x4 digital beamforming system, does about 12 dB better. 12 dB is, 9 dB is twice the range. 12 dB is significantly better, right? So our 4x4s right now, for example, today, does 3 times the range compared to any other Wi-Fi out there because it's using this kind of options in the standards. So just shows, animatedly shows that, you know, what is the difference between, let's say, a 11A and a G in range, throughput, and reliability. This is an 11A system. This is a 3x3 11N system, and this is a 4x4 11N system. Because of utilizing what I just talked about, it improves in all different dimensions. Now talk about 11AC. So 11AC, if I compare to 11N, added a few different improvements. And improvements are basically 80 megahertz channels. So you can transmit twice as much in frequency compared to what you did before. It also gives you the option to go to 160 megahertz or 280 megahertz channels. Again, it's just basically expanding the frequency usage. Gives you 256 QAM, much denser constellations. I will explain what that means. Increase the number of the streams you can transmit simultaneously over the air. It gives you multi-user MIMO, so I can talk to many users at the same time. And actually limited the options in the beamforming. You had 2 different types of beamforming before. Right now you have 1 kind. Talking about modulation, 256 QAM. It increases the phi rate by 33%. So if I was sending, this was the number of the constellation points I was sending over there, 64 QAM in the 11N. This is 256 QAM, a lot denser. Each one of these points represents a bit. Well, not a bit, a series of the bits, information. But you're sending a lot more information with the points closer to each other. More prone for error. So you have to have a very good signal to noise ratio to decode this. This puts some challenges on the design, and usually the channel doesn't allow this to happen. But Many vendors, including my own company, will do this because the customer values the big number on the box. Not necessarily will benefit from that, but it is something to be done, you know, for the competitive purposes. Multi-user MIMO. This is the most interesting part. Today, if I have one access point talking to 3 different stations, and those stations are inferior compared to my maximum capability, because either they're too far, or they don't have the 4-stream capability, or they are lower end. Still, what I have to do is I have to talk to them one at a time. I talk to station 1, I talk to station 2, I talk to station 3. That's a single user MIMO. So the time is shared between different users. In the multi-user MIMO, I stack them up. As long as the sum of them is equal to, let's say if I was a 4x4 MIMO that I could sell 4 stream, the sum of the 3 is equal to 4. There are 2 guys who can do 1 stream each and 1 guy who can do 2 streams. I can stack them up. So the total is 4 streams talking to them at the same time. This brings the overall performance higher and makes the access point to be able to communicate to the user simultaneously. This is one of the benefits that 11AC has added. If I looked at it a little bit more complicated, in this case, I'm talking to 3 different users at the same time, at the different times. I have to share the throughput. If the total network throughput was 866 megabits per second, each user gets 1/3 of that. But if a station number 3 requires twice as much as everyone else, and I can do multi-user MIMO, I can set this up that half the time I talk to station 3 and station 1 at the same time, and half the time I talk to station 3 and station 2 at the same time, going back and forth between them. That brings the total throughput to 1.7 gigabits per second. So almost doubles the throughput by doing this, if the stations were not able to reach the maximum on their own. If the stations could do 4 streams at the same time, it doesn't make a difference. But if the stations are doing lower number of configurations, it makes a huge difference in the throughput. If I was going to show you the throughput, the megabits per second of 11AC versus 11N, this is just as a baseline, it's a 4x4 11N. This is megabits per second. This is the distance or attenuation away from the source, how far away it is from the source. So as you go further and further, as you can tell by your Wi-Fi today, the farther you are, the megabits per second is lower. That's because of laws of physics, because the signal gets attenuated, your signal to noise ratio is lower, your signal to noise ratio lower, being that you can transmit less. So as I go further, the megabits per second comes down. This is for 11N today. With 3x3 11AC, I will gain something in the shorter distance because it allows the 256 QAM, it allows twice the bandwidth, and so forth. Twice the bandwidth is only useful in the short distance because you have to keep the same total power. So you actually reduce the density of the signal, but you double the bandwidth. When you go far, it's actually better to go to lower bandwidth and more power density. So this is a 3x3 11AC. This is a 4x4 11AC, which does better than 3x3 11AC. But the point is a 4x4 11AC converges with the throughput of 11N in the longer distance because you have to lower the bandwidth in order to make that happen. This shows why. In the short distance, I have 3 dB, I have twice the bandwidth. I can transmit more. This shows the efficiency of megabits per second for the different technologies. I go longer distance because of the 3 dB power disadvantage per subcarrier of 11AC compared to 11N. 11N starts doing better. And this is a 3x3 11AC. So the other issue, so the advantage of 11AC is that it gives you throughput in the short distance. It has multi-user MIMO. The disadvantage I talked about, in the longer distance, you will switch back to 11N, which is okay, because if you make 11AC, you have to make 11N as a part of the standard, so that it's a superset of 11N, so there's no disadvantage there. But the other problem is when you are using 11AC, which is 80 megahertz, you have less channels. So the people sharing you and your neighbors sharing the bandwidth together is more of an issue. So at 11N, at 40 megahertz, or I will say at 40 megahertz, 11N or 11AC, I have here 11 channels. In 11AC at 80 megahertz, I have 5 channels, and at 60 megahertz, I have 2 channels. That means that, if I want to share this with a neighbor who might be either at 80, 40, or 20 megahertz, I have to time share it with them, and the number of channels becomes less. One way of great thing about 5 gigahertz is that you have a lot more bandwidth that you have available, but with that is if you use them more, obviously you have less. So the probability of having a busy channel as a function of the users, if I looked at that for the 80 megahertz channel and the 40 megahertz channel, it is obvious that the 40 megahertz channel has less likelihood event of being occupied by someone else. If you have more channels, you have less likelihood event of being occupied. And that's okay, again, because the future products will have both options, and we can switch back and forth. But you have to be careful of that. Most of the time, you probably end up to be using 40 megahertz going forward, even though 80 megahertz is available. So now talking about some market opportunities. Not all devices have to be created equal. So I talked about there is various options, there are various ways of making a device. When you make a device for a cell phone, it's, oops, can I go back? Not that far back. Yeah, thank you. So when I make a device for a cell phone, does not have to be the same product as I make a device for a DVR or a set-top box. For the home, control devices don't have, they're totally something else. And they're all divided, there's actually 3 dimensions here. If you took the cost aside, which actually is a very important factor because consumers are willing to pay so much for each type of application, and some places they don't want to even pay for it. It has to just be given as part of the overall solution. But if you took the cost aside and look at this scientifically, you have throughput, you have range, and there's another dimension which is the power, which I don't have here. Those are the limiting factors. Those are the physical limitations that you have to deal with. So high bandwidth devices, multimedia devices, enterprise applications, they require the high throughput and the high range. And that's where we play. We play in the high throughput, high range. Then you got internet browsing. It needs a high throughput, but there's no way of testing the range. Most of the applications, you go buy a device at your electronic shop tomorrow, I bet with you on that box doesn't say anything about the range. It says the throughput, which is actually a consumer advertising mechanism because consumer doesn't understand there's another way of judging the range. Range is different in each home, but in reality you can judge it, but it's hard to communicate that to the customer. But it tells you this device can do 300 megabits per second. Doesn't tell you can do it only on 1 meter and dies out after that, but it talks about the range. And those are where most of the devices are sold, when you go about internet browsing and the basic consumer applications. Then you got the mobile devices, which is somewhere here. The throughput is not as important, range is not as important. It is somewhere in between. In the mobile devices, you have a very small screen. It's all about the power consumption and the cost. In that case, it's more about how long your battery lasts than watching a big screen TV out of your mobile, which you are not. You cannot do that. And the cost of burning the battery in 30 minutes is worse than having the quality there. Location-aware services, you walk into a shop, they want to recognize you and understand who you are so they can give you the advertising. It's about short range, short throughput. It's very small data communicated and it's usually not in a big environment. It's very local. Then home control and energy. Range is important because the whole home has to be networked. You have to send a small bits of data from your thermostat to your energy control unit, from your appliances and so forth, but the throughput is very low. So the area that I know best about is this area. This is where we expertise in, but doesn't mean that all the other products are not good. They're made for different applications. So one business case for this area is service providers. Service providers, actually, we're just going to start deploying in Russia in September, but service providers such as Rostelecom, or AT&T US, or Verizon and so forth in the US, They want to reduce their cost of operation when they deploy TV to people's homes. So video is a dominant traffic over the internet going forward, and that's the trend. And multi-room content sharing. So you have your DVR or master set-top box in one room. You don't want to duplicate that in every room, that you have the same device in other rooms. Basically, you want to take the content from one location to all the other locations. And that requires some connectivity. So the objective is that, to connect these devices inside the home in the most cost-effective format. The initial cost of wiring today in most of the world is prohibitive. In order to wire every device in your home, it is very expensive. And in addition, people change their mind. They want their DVR here today, they want it somewhere else tomorrow. They have to make choices in the beginning, which they have to overdo later. So if this is by a US service provider, I heard this directly from the chairman of a big corporation in the US. He told me that 10 minutes less on the work that their technicians do per home, 10 minutes less work is $30 million saving for them. So if they could make the life easier for them, it's huge service saving for the service providers. We believe that Wi-Fi is an enabling way to do this, and it will make a quick rollout to the multi-rooms, set-top boxes, and enriches the user experience and generates more revenue for the service providers. Also adds new services. The content that you're watching today is limited to the TV, which is wired. This is changing. There's a lot of services out there, such as Netflix, at least in the US, and so forth, or Google TV, that you can take your content with you everywhere. So your tablets are becoming your mobile TVs. You're not limited to that one TV you were watching before, and so forth. And Wi-Fi is the only interface which enables that going forward. So with the Wi-Fi, you're not going to be able to connect your iPad to the Ethernet. It's only Wi-Fi. And if Wi-Fi works better, that's where the services that they're looking at today coming together. In addition, the traditional service providers are looking to provide those services. They're moving away just from the fixed connectivity, fixed TV, and so forth. Can you click on that business case, please? This one. This is an advertising that you can see in US on TV. It is about a wireless TV.
Time for your high-tech
by AT&T.
The AT&T Uverse Studio. It's the classic catch-22. You want a TV in every room, but you don't want to have to drill holes or run wires. Well, now new technology is making it possible to watch your shows in any room in the house, even without a cable outlet, thanks to wireless boxes.
Let's Uverse this house.
This has got to be one of the most high-tech boxes to ever sit on top of a television. The only wires back here are running to the TV itself. Now we get to see the brains of the operation. This is sending that video signal.
This is sending the video signal Wi-Fi to the set-top box.
It's so much more convenient, and I love the idea of just being able to move the box to wherever we'd like to have it in the home or outside.
You don't have to drill holes, you don't have to run wires. We can keep the customers much happier without having cables running around their rooms.
Once they're installed, they don't have to stay put. So let's say you're having a big party, you want to put the TV outside, just bring the box out there. I'm Rich DeMiro, that's your tech report.
So that is one application as we're talking about, going to Wi-Fi. My own personal experience, about 5 years ago, I was trying to start a business unit for a company that did wireline communication. I moved around the world, talked to, I think that year I got actually pretty sick, and I flew for over 300,000 miles in 1 year, talking to different operators, trying to tell them about this wireline technology we're working at. Everyone agreed to it because they said that they don't believe the wireless can work. And they said, okay, wireline will be the best way going forward, assuming that wireless cannot work. If wireless worked, we will go do wireless. And AT&T, as they started deploying this thing, they're getting a very good results out of it, and it's getting better and better going forward with more products actually getting deployed starting this year in that domain. But wireless is changing. The image of the wireless is changing. Wireless was about convenience. It's becoming more and more about, it has to be about quality as well in order to get the applications going. It's not just about I can make my laptop and whenever it works, it works. It is about giving a service which is reliable and they charge for that service. So, talking about Wi-Fi, there were more than about 1 billion, close to about 1 billion chipsets of Wi-Fi sold last year. There'll be more than 1 billion chips of Wi-Fi being sold this year. The number of the Wi-Fi chips being sold is increasing year per year. It's becoming a dominant interface. So that's one of the reasons if this thing can work, and it can work actually, the good thing about it is, and one reason it's getting a good takeoff is, you can cater this to different applications by doing it differently based on different product needs. There were a lot of products sold in 2.4 gig. That's going down as a function of time. 11N is a dominant technology today, getting replaced with 11AC going forward. It is not the same Wi-Fi for every market. The trend and the pickup is not the same. The number of the units which is sold is not the same. This breaks down, is a market study which breaks it down based on the different products. You have phones here, which is going from 11N 2.4 to 11N dual band to 11AC. And you have the portable devices, PCs, tablets here, making the same transition over time. And then you've got access points and fixed consumer electronics over here. So with that, I'd just like to summarize that what was the point of this conversation and taking your time early morning today. So first of all, the point is that different applications will require different classes of the wireless connectivity. And the challenge is how to make that optimized and the best for that application. Wi-Fi has emerged as an enabling technology for wireless. And Wi-Fi allows this cost performance performance trade-offs for different applications. So wireless going forward is not going to be just about convenience. It's just more than data going forward. It's about quality of experience and reliability added on top of everything else. And wireless will spur new innovations going forward. You will see a lot more products, a lot more visions coming through, because now you can do things you couldn't do. You don't have to be stuck to that wire to the wall. So with that, actually I'd like to say a couple words about what we do and why we spend all this time and energy on this. And obviously, well, the why was before, but what we do. So Quantenna makes a 4x4 Wi-Fi chipsets. We have had great tractions in the service provider worldwide. We have the highest performance coverage and wireline reliability. If you can press on the link, I would appreciate that. This is an internal Verizon video for their own internal marketing. It shows what is the greatest technology, and it happened that we came across
today,
this whole product being shown
via
there.
coax to get the video signal. When we go to a media server arrangement, we now have the choice of using video over IP. And that IP can go over any LAN PHY layer in the home, including Wi-Fi. So with Wi-Fi, we're looking at some advanced capabilities in the new Wi-Fi technology. It's multiple antenna arrays using 802.11n standards that are greatly increase the distances and bandwidth performance on Wi-Fi. This is an 802.11n multiple antenna array Wi-Fi video access point. We're sending video here to our access point. It's a full resolution 3D HD image, 40 megabits per second, being streamed live. We have it set up on a cart, battery powered, and we're going to take it down to the hall to see how well our Wi-Fi signal performs as we increase the distance and the penetration through walls. We are now over 200 feet away from our originating signal access point. Our Wi-Fi signal is still holding up strong. Our video performance is showing no artifacts. We're also going through several sheetrock and steel walls. Pretty impressive, right?
So this is one of the ways to get into the future. By having products, we can provide that reliability and the video. So many carriers are using this solution right now, or are going to be using it starting this year going forward to provide services inside the home. We have been winning design sockets against the big guys like Broadcom or Qualcomm and so forth. And we were the first company who announced the 11AC 4x4 product. Most important thing is we're starting our R&D center in Russia. Actually, we are funded by, in addition to many different VCs that we have Rostano funded us and Bright Capital. Where's Bright? Actually, Bright was here. They came out because. Do you see Bright? Okay. And Bright Capital. Anyway, so there are two Russian VCs have funded us, and we have raised about $160 million in capital funding so far. So that's all I have. I really appreciate your time. Sorry to keep you busy Saturday morning. Thank you. If you have any questions, I'll be more than happy to answer.
No questions?
Thank you for the presentation. I'm just a consumer of Wi-Fi devices, and I want to ask you, you talk about range, about flow, yeah, but what about energy consumption for the mobile devices? It's, I think, a very important question. We have many, especially for Android, they have a very little battery, and for how, with the comparison with the M, the new AC is.
Sure.
Thank you.
Sure. So,
hello.
So the new AC, I guess your question was, how does M compare to 11AC on the battery usage, correct?
Yeah.
11AC will be better. When you use a bigger bandwidth, a bigger hertz bandwidth, you can send twice as much throughput, and then your computational, at least your the number of transmit antennas don't have to increase and so forth to get that throughput. And then usually your power consumption is dominated by your power amplifiers. You have less of those to do the thing. So for the shorter range, for the mobile devices, if you want to send something very much through, the fastest way possible for a shorter range, not considering the range, 11AC will be better. There is no doubt there. So there is a set of different options again to mention. Not all these devices are going to, all these options are going to fit every device. If I was going to make a mobile device, I would think very differently than if I was going to make an access point. But if it did have a strong access point, it will get the best out of the mobile devices without putting a big constraint on the mobile device.
Thank you.
Thank you, Sam. Actually, I'd like to ask you about another technology which is called long-term evolution. LTE is already built in the new iPad, which was presented earlier this year, and it will be probably built in new iPhone.
That's right.
Which just coming this year also.
Wi-Fi.
Yeah, how do you see the joint life of LTE and Wi-Fi?
That's a very good question. I'm not an expert in LTE, but
You're expert in this market, right?
right. But LTE is a licensed path. So my wife has a iPad. If I was going to use the LTE, you have to pay for a service. I cannot put the LTE inside my DVR or a set-top box. The video you just showed, when it shows the set-top box working with an access point for the inside the home applications, then the LTE is not going to be used there because I don't want to pay $10, $15, $30, $50 or 1,500 rubles per month to just make sure my DVR is connected to my TV with a high throughput. I'm taking a great resource. There's going to be about, I think, 2.5 billion chipsets sold by 2015 in Wi-Fi. There's going to be 1/5 of that in LTE. Because for every device you have one phone or maybe one iPad which might have LTE. You have many devices inside your home, your laptop, your access point, your TV, your set-top box, which will have Wi-Fi. So they're going to coexist. As a matter of fact, we are pretty excited about LTE. And why is that? Because LTE, already we know that because of using more bandwidth to transmit, is going to be constrained by the number of the users who will use it simultaneously. So when they are deploying LTE today, they're putting a Wi-Fi next to it in those small base stations for the offload. So when the network is congested in the train stations, in the hotspots and so forth, you have the choice of using the Wi-Fi for data communication, and you bring the strength on the network lower. I think LTE is a great technology, it's going to exist, but I don't think it's going to replace Wi-Fi. And they're complementary.
Hello. I'm sorry, why haven't you mentioned more than 4-4 devices? Is it number really optimal for some computational reason, or is it just technically more convenient to do such devices?
4x4 versus other devices, and you're asking, I guess, why they're not more of them out there?
More than 4-4.
Oh, more than 4x4?
Yes.
Oh, good
Yes.
question. Okay.
About more.
Okay. So there's two reasons for that. Reason number one is that Wi-Fi standard only goes up to 4x4. It did not make the standard for more than 4x4. Reason number two is, as I mentioned earlier, you're going to be limited by the diversity of your channel. So if the rank of the channel is not greater than 4, having more than 4 allows you to guarantee that 4 is a good thing, but usually the rank of channel is between 2 to 3. Having a 4x4, actually what it does is, at least based on our experience, when we have a 4x4 device, 99% of the time, we guarantee 2 streams. About 40% of the time, we guarantee 4 streams. If you have a 3x3 device, 40% of the time, you guarantee 2 streams, 90% 2 streams. So if you compare them, 3x3 does half the performance of a 4x4 because it guarantees 1 stream, 4x4 guarantees 2 streams. It's not about actually guaranteed 3, 4, 5 streams going up there. But the standard didn't allow it. That was one. They didn't think that channel diversity would need that. 11AC allows 8 transmit, 8 receive. Again, 4 streams to each user, not 8 simultaneously to this given user, but 4 streams to user 1, 4 streams to user 2. So for the access points in the 11AC, there will be 8x8 in the next generation. I would say that probably by 2015.
Okay, so that's it. I think. Thank you once again.
So thank you.
Thank you for coming. Okay, and